For this lesson, we're going to be looking at the inverse of a function. So let's start by talking about what the inverse is. So the inverse of a function is the reverse of the original function. So basically, it undoes what the original function did. The easiest way to think of this is think of it as an action that had a result, and the inverse would be undoing the action in order to undo that result. That's the idea of what the inverse is. The way to think of this is if I have a relation and its inverse, my domain and range are going to flip, basically. So here I have -3 in my domain and 4, which corresponds to the ordered pair -3, 4. Now in my inverse, my domain and range are going to switch. So it basically does it backwards in a sense. So now my domain will be 4 and my range will be -3, giving me the ordered pair 4, 3. So let's get into some examples of how to use this and how to find the inverse, because the examples will really help you to understand how to use this. So for example 1, we're going to be finding the inverse by interchanging coordinates, similar to that first example we had in our definition. So for this example, we're going to find the inverse, f, and this -1. So when I denote inverse, I always use this superscript -1. And again, how we say that is just f inverse. So we're going to find the inverse, f inverse, of the relation f, whose ordered pairs are 3, 1, 4, 2, 5, 3, and 6, 4. So when we're finding the inverse and we have some ordered pairs, we can just swap our x and y coordinates. So my inverse is going to be 1, 3. So I just swapped those two. 2, 4. 3, 5. And 4, 6. So all I did is for every ordered pair, I just swapped my x and y coordinates and got my new inverse coordinates. For this next example, we're going to find the inverse again of relation f, whose ordered pairs are -2, -8, 0, -2, 3, 4, and 4, 7. And then we're going to graph both of these. So for this example, I'm going to do a table of values just to give you another way of seeing these written out, and it will make it easy for graphing. So let's start with our relation f. So I'm going to start with my table of values here, x and y. So my first ordered pair is -2, -8. Then I have 0, -2, 3, 4, and 4, 7. And now I'm just going to graph those onto my Cartesian plane over here. So we had -2, -8, 0, -2, 3, 4, and finally 4, 7. Now let's take a look at the inverse. So again, how we denote inverse is f and then this little -1 there. So we'll make our table of values, x and y. And remember, we're just going to switch the x and y for each individual ordered pair. So the first one was -2, -8, and now it will be -8, -2. The next one, 0, -2, switches to -2, 0. And then for the next one, 3, 4, we'll switch to 4, 3. And finally, our last one goes from 4, 7 to 7, 4. And now let's graph that. So we have -8, -2, -2, 0, 4, 3, and finally 7, 4. So that just gives you an idea of how these different inverses look. Let's do another example. So for example 2, we're going to be finding the inverse graphically. And once we find the inverse graphically, we're going to graph it. And then we're going to find out if the inverse is a function. So let's start by finding the inverse. What we're going to do is we're going to find some nice points here. So I'm going to start with my first nice point on my parabola, and that will be 0, 0 right here. And then I'm just going to switch the coordinates. So if I switch 0 and 0, I still get 0, 0, and we'll put a dot there. Let's find another nice point. So the next one would be 1, 1. Again, if I switch 1, 1, still 1, 1. So we can just put a dot there. Next nice point will be at 2, 4. If I switch that, that's going to go to 4, 2. So that point lives right here. Let's do the other side of the parabola now. So we have negative 1, 1. If I switch that, that will be 1, negative 1. And then I have negative 2, 4. And if I switch that, that will be 4, negative 2. And because these were connected originally, we can connect them again. So I'm going to do my best to make this look okay. It's kind of hard on the iPad, but it will look something like this. Next, it asks us, is the inverse a function? So because we have a graph here, we're going to use our vertical line test. So we draw a vertical line, and we're going to picture this line moving and sweeping across our whole curve here. And right away I notice that it's touching my curve at 2 different points. So what that means is because it's touching it twice, it means it's failed the vertical line test. And then I can say that it is not a function. And it's because it fails the vertical line test. So in this case, we have a function to start. We know a parabola is a function. And then we have our inverse, and it is not a function. Let's try another one. So for this next one, we have this nice little line here, and we're going to start by finding the inverse of it. So we'll start by finding some nice points. So this first one here is negative 2, 7, which swaps to 7, negative 2. We can't fit that on our graph here, but that's not a big deal. We'll leave that one out. We'll still be able to figure it out with the rest of the points. Then we have negative 1, 5. When I switch that, I'll get 5, negative 1. So let's put our point right here. Then we have 0, 3. When I swap those, I'm going to get 3, 0. So our point goes right there. Then we have 1, 1. When you switch that, we get 1, 1 again. So let's put our point right here. And then our last nice point we have is 2, negative 1, which will go to negative 1, 2 right here. And because it was connected in a nice line originally, we can connect the points again. So I'm going to try my best. I can't use a ruler, so it's going to be a little squiggly, but that's okay. So there is our inverse. And next we want to figure out if this is a function. So because we have a graph, we're going to use the vertical line test again. So I'm going to draw my vertical line. And I want you to picture it sweeping across the whole picture. And if you notice here, it's only hitting my graph one time. And as it sweeps across the picture at any given point, it will only be hitting my graph once. So what we can determine is that it is a function, and we always need to write our y. So it's because it passes the vertical line test. Now let's make a bit of a conclusion here. In this case, my inverse is a function. In my last case, my inverse is not a function. So unfortunately, there is not necessarily a connection there. It can be, sometimes it's not. So it is important to determine using the strategies that we talked about in our first lesson to find out if it is a function or not. Okay, our next strategy to finding the inverse is my personal favorite one to do it, is by finding our inverse algebraically. So the first thing we're going to do is we're going to look at our function here, f at x equals 5x plus 4, and I'm going to replace f at x with a y. So I'm going to rewrite it as y equals 5x plus 4. So all I did is instead of writing f at x, I just wrote y, kind of like how you saw it back in grade 9 and grade 10. Now we're just going to swap my x and y value. So instead of writing a y, I'm going to write an x. Instead of writing an x, I'm going to write a y. They're just trading places. Finally, I'm going to isolate y. I'm going to get y all by itself and have it be y equals. So we have x equals 5y plus 4. We want to get that y all by itself. So we want to get rid of stuff that's far away from my y first. Let's move the 4 over to the other side. And now let's divide out that 5. So we divide by 5, divide by 5, and we'll have x minus 4 over 5 equals y. And that would be our inverse here. Let's try our second example. It's a little bit trickier. So for this example, we're going to first find the inverse of the function f at x equals x squared minus 5. So let's start by, instead of writing f at x, we're going to write a y. And then I'm just going to swap my x and y. So if x equals y squared minus 5, and then I need to get that y squared all by itself. So I'm going to start by moving this 5 over. And then I don't want y squared, I just want plain y. So I'm going to square root on this side, square root on this side. So I have plus or minus the square root of x plus 5 equals y. And the reason I have this plus or minus is because whenever I square a number, I could have squared the positive number or a negative and we'll get the same answer. So for example, if I have negative 2 squared, I get 4. And if I have 2 squared, I also get 4. So because of that property, it's important we put this plus or minus here. Now the second part of the example says, is the inverse of f at x a function? If not, we'll restrict the domain of f at x to make it a function. So if I think about this, I want only one y value for every x value. In this case, I'll do a little example here so you can see it. It's a little bit easier. I'm going to plug in, let's say, 4 for x. If I plug in 4 for x, I would have plus or minus the square root of 4 plus 5 equals y. So that would give me plus or minus the square root of 9. So we'll get plus or minus 3 equals y. So in this case, my values for y would be 3 and negative 3. So because I have these two values for y, this is not a function. So what we'll write is that the first part, this is not a function. Because there are two y values for each x value. And again, that's because of that plus or minus situation. Now, the next thing is, if it's not, we want to restrict the domain of f at x to make it a function. Now, if I think about it and I have all of my x values, what I can do is I'm just going to take the positive ones. X is bigger than or equal to 0. That way, I will just get rid of the negative ones and just have the positive ones. Okay, so let's try a application problem here. So for example 4, we're going to be using the inverse to solve some problems. So for part A, the temperature below Earth's surface is a function of depth and can be defined by T at D equals 11 plus 0.015 D. So the first thing we're going to do is we're going to state the domain and range of T of D. Now with these kinds of word problems, I find it easiest to draw a little picture to help us understand what's really going on. So this is what our graph's going to look like. So it's a line. We have T and D, and our y-intercept is at 11, and it's going to be increasing because we have a positive slope like that. Now, if I think about this, D at 0 right here is going to be the surface of our Earth. So that's what we're going to write, that we're just assuming that. Assume D equals 0 is the surface. And as we continue to increase our distance, our temperature is going to get warmer and warmer and warmer. So if we're thinking we start on the distance and we continue to increase our distance, our domain is going to be that our distance is an element of real numbers such that our distance is bigger than or equal to 0. And the reason why it's bigger than or equal to 0 is because I start at the surface and I'm continuing from that point and I'm adding on distance. Next, for our range, because we're going to the center of the Earth, it's going to be getting hotter and hotter and hotter. So our temperature is also an element of real numbers, and our temperature has to be bigger than or equal than 11. So it's going to start at 11. That's our surface temperature. And as I get closer to the center of the Earth, it's going to get hotter and hotter. There's no situation where all of a sudden it's going to get colder in the middle. Now let's determine the inverse of the function. So what we're given is T of D equals 11 plus 0.015 D. Now, the first thing I'm going to do is instead of writing T of D, I'm going to write a Y. And just to simplify things here, instead of writing a D, I'm going to write an X, just to symbolize our independent and dependent variables. And now I'm just going to swap that X and Y. So X is going to come over here, and my Y is going to go over here. Now, let's isolate Y. So the 11's got to move to the other side. And now we're just going to divide out that 0.015 from both sides. And we'll get X minus 11 all over 0.015 equals Y. So that's our inverse there. And because I've done the inverse, the way that I can write it with my proper variables is going to be D of T instead, because it used to be T of D, and now it's swapped. And that will equal T minus 11 all over 0.015, because I swapped those two variables. Okay, so let's state the domain and range of this again. So our domain and range will be the same. So our temperature at the surface is still 11. So it's not going to change that all of a sudden our temperature in real life is different. So my temperature still cannot be lower than 11. As I go closer to the center of the Earth, it's going to get warmer and warmer. Same with my distance. My distance at the surface is 0, and as I increase towards the center of the earth, my distance is going to increase from there as well. Now, what does my inverse represent in a real world situation? So in this case, I would be trying to find the distance for any given temperature. So if I gave you a temperature value, you could say, oh, that temperature occurs this many meters into the center of the earth. That's the idea. So how I can write that in words is how far down we have to go. How far down you must go to reach a certain temperature, or reach a specific temperature. There we go, and that's our first full word problem. So there's one more word problem here that I want you to try on your own, and the full solution will be posted on Classroom for you to take a look at.